Chem students, this is number 21 in your gas stoichiometry notes. I'll do both A and B. There is a limiting reactant question on this. So just two different questions here. Neither one of these is at STP. Well, second one's at STP, sorry. First one's not, second one is. So here's your reaction. This is actually the burning of propane, combustion of propane. Notice there's 1 mole of propane for every 5 moles of oxygen, makes 3 moles and 4 moles of those two things. So it's telling you have 125 grams of propane being burned. So we know this is 125 grams. And we want to know total liters of gas that would be produced. Well, if we think about things that are going to be produced, this is not being produced, it's being used. That's being made, that's being made. And they're both gases. Okay, they're both gases because it's at 100 degrees Celsius. So we want to know total liters of these, but they're not at STP. Okay, total liters, not at STP. So they're at this pressure and this temperature. So we're going to have to do a little PV-nRT at some point in time. So here's kind of your process here. I want to get from my grams of this, figure out how many moles of these things are made, and then I can plug those moles into PV-nRT and figure out how many liters it'd be. I cannot use the 22.4 liters because we're not at STP. So we start with our 125 grams of propane. Go grams to moles of propane, which is, off the periodic table, is 44 grams. 3 carbons and 8 hydrogens would be 44 grams. So those labels cancel. Go to our ratio. This is where it's going to get a little bit strange here. I'm going to say for every 1 mole of propane that burns in this reaction, if it wanted one of these individually, I would do either 3 moles of carbon dioxide on top or 4 moles of water. It wants total liters, so let's just do total moles, because moles of gas all take up the same amount of space at the same temperature and pressure. So for every 1 mole of propane that burns, we make 3 plus 4, 7 moles of gas are made. 7 moles of gas are made. Now I cannot go 1 mole equals 22.4 liters because we're not at STP, so we're going to get our moles and then plug into PV-nRT. And when you get your moles there, you get moles of 19.9 moles of gas. 19.9 moles of gas are made in that reaction. Now, some of those moles will be carbon dioxide, some will be water. More of them will be water than carbon dioxide, but that's how many total moles there are. So now I'm going to take those moles and plug them into PV-nRT and solve for the volume. Okay, see what the total volume would be in that situation. So pressure is 1.2 atmospheres. Trying to solve for V, 19.9 moles. R is always 0.0821. And temperature has to be in Kelvin, so plus 273 would mean 373 Kelvin. Multiply, divided by 1.2. I got a volume of 507.5. How many total liters of gas would be made if you burned 125 grams of propane in your grill or whatever it was? Get that many liters of those. Obviously, more of those liters would be water than carbon dioxide. All right, there's the first one. 21B, limiting reactant question. Okay, same reaction. I'm going to pause this right now and rewrite that reaction up there so we've got it. All right, back on there. So it's telling you this is at STP. So you got 50 grams of propane, 157 liters of oxygen. That's how much you have available. Okay, one of them is limiting, one of them is excess. So let's turn those things into moles and see if they're in a 1:5 ratio. This needs to be 5 times more than this in terms of moles. So let's take our 50 grams of propane, 50 grams C3H8. Again, the periodic table, add up that and is 44 grams per mole. And for propane, that is 1.14 moles. Do the same thing with oxygen, but it is 157 liters. 157 liters of oxygen. Since we're at STP, we can say there's 22.4 liters per mole of oxygen. So we'll get that into moles. It's about 7 moles. Well, the oxygen is supposed to be 5 times bigger. 7 divided by that is close to 7, okay? maybe 6 something. So this is more than 5 times bigger, meaning there's more of this than we need. That means this is our limiting reactant right here. Okay. There's our limiting reactant. We could do a little BCA table. Okay, we could do a little BCA table. I'm going to kind of erase this and do a BCA table. So if I go here, so I'm going to just kind of work my way down. So before this was 1.14 moles, this was 7 moles, those would be 0, those would be 0. Now we're going to try and figure out how many moles there are of everything on there at the end of the reaction. So moles of everything. And I probably figure out how much excess there is of the oxygen liters. So again, this is going down by 1.14 because it's my limiting reactant. So I know there's none of that. That's my change. That's how much is there after the reaction, before changing after. To get from here to here, it's a 1:5 ratio. So take this times 5, that times 5, which is, I don't have that. Give me a second. All right, back on. That times that is 5.7. Remember, that's how much oxygen would have been used. 7 minus that is 1.3 moles of excess oxygen. Okay. Again, on this side, that's a 5:3 ratio, so that's tough. Here's a 1:3, so multiply this by 3. We'll tell you what that is, which would be going up by 3.42. So that means there's 3.42 moles of CO2 made, and a 1:4 ratio, so 1.14 times 4 is going up by 4.56. So there's 4.56 moles of that. Okay. Now I could have asked you, out of these 157 liters, of O2, how many liters there are excess? Well, there's 1.3 moles of excess, so I could go, well, 1.3 moles, and every mole is 22.4 liters, and that would tell me my excess, which is about 29.3 liters of excess oxygen that would not be used out of the 157. All right, have a good day.